From some of these chemical elements, many soon split, including potassium, sodium, barium, calcium, strontium, lithium and magnesium by Humphrey Davy in the early 1800s. He also realized the electrical resistance of cables emitting sparks of light. And it was Simon George Ohm whose name represents to calculate the resistance. One time Thomas Alva Edison used it as the forerunner of the lamp. Edison only added a glass wall filled with argon gas to preserve the filament. Applying the battery with copper wire is the next experiment.
Here's a metal bolt which is not a magnet. It's made up of magnetic domains, but they are pointing in random directions. Now let's take a wire, wrap it around several times, and then create a circuit. The current through the wires forces the magnetic domains to line up. That means we've just made a magnet, or more specifically, an electromagnet. It can do the same things that a permanent magnet can. It can pick up pieces of metal, and it has a north and a south pole which will attract or repel other magnets. But the electromagnet is special in the sense that it can be turned on or off, just like the light bulb. You can't do that with a permanent magnet. Now watch what happens when we flip the battery. The electric current was flowing this way, but now it flows the other way. This will cause the poles on our magnet to switch places. North will become south, and south will become north. This is called reversing the polarity of an electromagnet. Instead of flipping the battery, an easier way to do this is to just switch the wires. You should be aware that the electromagnet will get very hot if it's on for a while. Just a caution in case this video inspires any science projects.
André-Marie Ampère said this is the law of electrodynamics. His name is immortalized in units of electric current. Ampere creates magnetic energy from electrical energy. You can also see other electromagnetics in atomic theory. The circulation of celestial bodies. The use of coils not only converts electrical energy into magnets but also vice versa. Michael Faraday, 1831, a student of Humphrey Davy, invented the dynamo or generator. This discovery is the initial concept of the creation of electricity, namely generating electricity from the energy of motion.
And vice versa change electrical energy into motion.
Let's take one of our permanent magnets and drill a hole in the center and put it on something that will allow it to spin. Now bring another magnet towards it. Our spinning magnet will immediately line up until opposite poles are right next to each other. Now switch out the side magnet. The same poles repel and opposite poles attract. If we keep switching out these side magnets, then our spinning magnet will just keep spinning. This concept of the spinning magnet is really important. Let's come back to our spinning magnet. This time we'll replace the spinning magnet with our electromagnet. As soon as we connect the wires, the magnet turns on and it lines up with the side magnet. Now, in reality, connecting these wires would prevent the bolt from spinning freely, but what's important here is the concept of the spinning electromagnet. Now let's switch the wires to reverse the poles on the electromagnet. The same poles repel and opposite poles attract. Now reverse the polarity again. Same poles repel and opposite poles attract. If we keep switching the polarity, our electromagnet will just keep spinning. To make this stronger, let's bring in another permanent magnet on the side. Notice how this side has the south pole towards the center, and this side has the north pole towards the center. The side magnets work together to spin the one in the middle. This right here shows the very basics of an electric motor. But we need to make a few improvements. The two side magnets can be replaced with stronger curved magnets. And instead of a bolt with wires, we're going to use a metal loop. This is called the armature. Connect our wires and we have a circuit again. This time you can think of the electromagnet as flat like this with the south pole pointing up. Now the armature will spin until opposite poles are lined up. We can keep it spinning by switching the wires just like we did before. But this is a lot of work to sit here and manually switch these wires. We need to add something to the armature called a commutator. It's a ring with gaps on the opposite sides. The commutator will spin along with the armature. Now we connect the circuit with 2 brushes on the side. These brushes will slide along as the commutator spins, and they are spring-loaded so that they always maintain contact. The current flows from the wire, through the brush, the commutator ring, the armature loop, and back through the other side. Now we have our electromagnet and the armature spins. As we come around this time, the brushes will switch contact to the other side of the commutator ring. Remember, there's 2 brushes, so this is happening on both sides. Before the switch, the current in the armature is flowing this way. After the brushes switch sides, current will flow the other way. This means the electromagnet switches polarity, which will cause the armature to keep spinning. This commutator ring does the same thing as switching the wires like we were doing before, but this time it does it all on its own. It will continue to spin as long as we're connected to a battery. Disconnect the battery, no more electromagnet, and the spinning stops.